Hey, welcome back once again. This time we'll see how a MOSFET behaves when there is an inductive load with its gate to source voltage, drain to source voltage, and drain current waveforms. So let's start. We saw in our last videos that MOSFET has parasitic resistors and capacitors. I recommend you to watch that video first. If you have already watched that video, please skip to this timestamp. For starters, we'll brush on the parasitic components of the MOSFET. When we see a MOSFET, there are capacitors between gate to source, gate to drain, and drain to source, and resistance at drain, gate, and source. The gate to drain capacitor is called as mirror capacitor. The gate to source capacitor and drain to source capacitor stay constant all the time, but this mirror capacitor changes when the MOSFET switching occurs. This mirror capacitor is low when the MOSFET is turned off. When we provide VGS, MOSFET turns on, and VDS decreases across the MOSFET, and current starts flowing through it. When the MOSFET is turned on, the gate to source voltage increases and drain to source voltage starts decreasing. There is a point where VDS becomes equal to VGS, and at that point, the mirror capacitor value increases to approximately 10 times of its previous value, which plays an important role, and this information is very useful for understanding the switching of the MOSFET. The input capacitor is tentatively equal to the mirror capacitance plus gate to source capacitor, and output capacitance is tentatively equal to the mirror capacitance plus drain to source capacitance. In previous video, we have seen the behavior in the circuit due to inductor switching. In that, we saw why do we need a freewheeling diode and what is the reverse recovery of this diode. Please watch it by clicking on this card above. Now let's take this circuit. MOSFET is switching this inductive load and it's being used as a low side switch. We'll see the gate to source voltage, drain to source voltage, and drain current waveforms of the MOSFET while it is turning on and turning off. We'll divide this operation in multiple time periods. Before we start, we are considering that the inductor was discharged to this diode at the previous turn-off process of the MOSFET. So while turning it on, this diode will exhibit reverse recovery characteristics in the circuit. At time t0, we give a gate to source voltage to the MOSFET, which increases gradually, and it charges the input capacitor of the MOSFET with internal resistance of the driver circuit. At time t1, the gate to source voltage of the MOSFET reaches to the threshold voltage, causing current to start flowing in the drain. In period t1 to t2, the drain current increases in proportion to the gate to source voltage, but drain to source voltage stays constant due to this diode. At time t2, the MOSFET carries the entire load current. In this, the reverse recovery current of the diode is also added, so the drain current increases further. At time t3, the drain current reaches the maximum value. Up to this point, the drain to source voltage of the MOSFET stays the same level as operating voltage, and gate to source voltage of the MOSFET reaches a value capable of conducting the peak current generated in the transistor. We can call this the polarity reversing point of the reverse recovery current of the diode. In the period T3 to T4, the drain to source voltage decreases and reverse voltage of the diode increases by the same amount. Normally, the drain to source voltage decreases at the same rate as the mirror capacitor of the MOSFET is discharged depending on the gate drive voltage. And gate to source voltage remains at the same level throughout the MOSFET turn-on process. But change in drain current due to decrease in reverse recovery current of the diode affects the switching process. If the drain current decreases, the gate source capacitor is discharged via mirror capacitor, and gate to source voltage value decreases to the value sufficient to conduct the drain current. Consequently, a sharp drain to source voltage waveform is generated during this period. Well, This sharp change in drain to source voltage causes so many problems. Let's say the load here has a low resistance. In this case, a very large amount of drain current will flow. The change in commutation of free wheel diode also increases, which might generate high reverse recovery current through the diode, which reaches the maximum value and then decreases suddenly. Due to this, excessive voltage may increase within the circuit, which eventually result in over-voltage breakdown. So this change in voltage with respect to time has a very adverse effect on the MOSFET, which is called as the dV by dt rate of the MOSFET switching, which we will see in the future video topics. At time t4, the mirror capacitor increases and drain to source voltage decreases further. At time t5, the input capacitor charges fully to drive the MOSFET. The MOSFET resistance further decreases, and at time t6, the RDS on of the MOSFET reaches the lowest value and MOSFET is finally turned on. This is how a MOSFET turns on when there is an inductive load. Now we'll see the turn on process of the MOSFET. To turn off the MOSFET, we remove the gate to source voltage from the MOSFET and discharge the input capacitor through the internal resistance of a driver circuitry. So VGS of the MOSFET decreases. The MOSFET acts as a mirror integrator having a large mirror capacitance. The drain to source voltage of the MOSFET shoots up in the T9 to T10 stage. The freewheeling diode starts conducting at time T10. The drain to source voltage is maintained at constant level, and the drain current decreases in proportion to the gate to source voltage. The gate to source voltage decreases to the threshold voltage at time T12. The drain current is completely down and input capacitance is discharged fully. If we see the turn on time of the MOSFET by zooming out these waveforms, these time periods seems very small in front of it. Well, this is how a MOSFET works when there is an inductive load. Next time, we'll see some more interesting facts about MOSFET switching. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.